let's talk about a different philosophy of CPU design here. Yeah, let's. It's better to show the example. Intel Ice Lake. It's pretty nice architecture. Um, well, it brings pretty decent 18% IPC according to the spec benchmark, and it's pretty nice lift up, no doubt about it. But the problem starts here because Ice Lake is 30% bigger in terms of transistors than the Comet Lake, and this leads to the decreased efficiency because more transistors are burning more power, and maybe if they use a dark silicon, maybe not that much, but still you are kind of wasting a lot of transistors. And let's compare it to the ARM Cortex. This is different philosophy. And this is what I was explaining with the Apple cores. Like they increase more IPC, they bring every generation more IPC with less and less transistors. And look at here, IPC increased 20% and the transistors went up only 17%. So this means they really increased efficiency. So the IPC per transistor actually increased. So this is totally opposite way in compared to Intel. Intel is actually every generation like losing efficiency. For every IPC, they need more and more transistors. So actually the performance, the IPC per transistor is actually decreasing. And this is really major difference in the CPU philosophy design. Uh, and even more, you can see, look at the Cortex A78. It was released this year, and they increased the IPC by 7%, but they decreased the transistors by 5%. This is absolutely, I would say, devastating. Even there is no devastation performance, but the performance per square millimeter is absolutely devastating. And this is one of the problem for the servers, because I will compare it to the with the Zen 2 architecture, this 2 ARM Cortex. I will explain that this is really serious trouble for x86 actually. But anyway, it leads to the worst thermal, the efficiency, it goes more and more thermal overheating actually. And to avoid the thermal overheating, you need to spend some more dark silicon, like a more cachy, something which doesn't make so much heat, but it helps to spread the heat into the heatsink. So actually, the wasting transistors by not really good design here, it leads to wasting another transistors to solve the issue with the overheating. And I also seen a lot of people was talking the IPC cannot scale linearly. That always it costs more. But yeah, in x86 world maybe, but this ARM architectures, it's like this is the evidence that you can do it actually. You can increase more IPC than transistors count, and this is just, I don't know. We can talk about it about the reasons why, and it's some people say the transistors are cheap, so maybe that's why the x86 designers they really use this rule, and they're like every new node you have almost twice more transistors available, so we can actually design less and less efficient CPU, right? So you have a lot of die space there, but actually the transistors are not cheap, because every new node is really more and more expensive. So I don't think so this is the case. And the another thing is like we need more dark silicon to help spread out the heat. It's like a no. It's just this is not curing the the problem. The primary problem is not the overheating chip and try to compensate the heat, and the overheating. The problem is that you need to actually develop more efficient architecture. When you develop something inefficient, yeah, you need to suffer from the thermal overheating, and you need something like a dark silicon and other techniques. But it's the cause of the wrong, no, I'd not say wrong, it's like different philosophy of the CPU architecture. And it's more evident in actually servers. And let's compare the Zen 2 with those ARMs. And you can see the Zen 2 has an area 3.6, as we've seen on some other slide, and including, of course, the half megabyte L2 cache. Now let's compare it to the same Cortex A77, guys. And the area of this chip is 1.4 square millimeter. 1.4, and also including half megabyte L2 cache. And you can see the IPC is about 3% above Comet Lake, and Zen 2 in the Geekbench has the same 3% over Comet Lake. So in terms of IPC, they are really equal. Even like probably Zen 2 is faster in the floating point heavy loads, and Cortex is faster in the integer, but in Geekbench benchmark is approximately equal. But the problem is that look at the area difference. Zen 2 has a lower density due to high frequency design. This is correct. If AMD would manufacture a Zen 2 core with a high density, the same way like the ARM Cortex, yeah, the numbers would be different. And from the other side, we know that if we do, we would end up with a 2.2 square millimeters. But still, it's like still 57% bigger than A77, guys. This is the problem. And this is the also higher consumption, it means. That's a problem, because ARM can put like at least 60% more cores in the servers. This is the huge problem in the servers, especially. Maybe not problem for the desktop, but for the servers, when you need to put 100 dice or maybe 160 dice. Yeah, that's actually answer why actually the Graviton 2, the Amazon chip, using Cortex, the older one, NeoVerse N1, based on the Cortex A76, the older one. The area of this core is also 1.4 square millimeter, but using 1 megabyte cache. But they can make actually the monolithic 60 core server CPU, and is actually they are destroying the Zen 1 architecture, and the Zen 2 ROM has big problems with it, actually big problems, and in some parameters losing. For example, in parameter like performance per one thread, it's actually losing against this ARM chip. Even the A76 has a lower IPC than the Zen 2, like a 20%. But because there is no SMT, it's actually winning, even using lower frequency, because Zen 2 is like a 3.3 gigahertz, and this ARM chip, the Graviton, is usually using it's running fixed frequency 2.5, I guess. And yeah, but Zen 2 cannot make AMD cannot make a monolith 64 core chip, because it would be too big, and it's actually not possible. And but ARM and the Graviton is really monolithic 64 die, because if you calculate 64 multiplied by 1.4, it's like about 90 square millimeters for 60 core bit 64 chip. So this is really huge savings, and here really starts to be problem for AMD in the servers and also for Intel, because if you look at the Cortex A78, it's even worse. If we don't calculate the lower density here, with the normal density is right now the Zen 2 versus Cortex A77, it's like 2.5 more cores per square millimeter, or it's the same die size, and it's a problem. Where AMD can put maybe 12 cores on the one chiplet, or eight chiplet, let's say, the ARM can put on the same chiplet, the same die size. They can put 16 is like 20, yeah. They can put 20 cores to the same die size as AMD can put only 8. And with the same IPC in the servers, guys, this is really big trouble in the server. And A7, the Cortex A78, the new one, it goes even 2.9. Also including there is a higher IPC than Zen 2. But actually the core is even smaller. So it goes the scale up, they can do 3 times more. So instead of like instead of 8 core chiplet, they can make a 20 core chiplet, a little bit smaller than the Cortex A77, but with a higher IPC, like a 7% over Zen 2. So the overall performance per square millimeter is almost 3 times higher. And yeah, this is problem for Intel and AMD right now, because those ARM chips, like every ARM chip is dangerous, because this is the efficiency. Every ARM chip needs to increase IPC more than the transistors count actually. So every ARM chip is from naturally it's more efficient and delivers more performance per transistor. Just better architecture. And this is dangerous, especially for the servers. But yeah, Apple will destroy every laptops and most of the desktops with this philosophy, and I don't think so that x86 has a solution in the short term. I think before they might happen that AMD might go bankrupt again. They might have a big trouble, because speaking about the AMD K12, they really did a really big mistake, because probably Jim Keller was mentioning this, and he was predicting this behavior, and he was probably telling them, okay guys, we should maybe concentrate to efficiency a lot. We should maybe think twice before we spend some transistors. We should maybe forget about the high frequency designs, because we should really concentrate to low frequency but high IPC designs, because if we don't do that, there is coming something really bad from the Apple and also from the ARM Cortex cores, because they are really pushed. Because the philosophy of the efficiency for the smartphones is really pushed this way, and if x86 will not actually follow the same efficient way, they are going to be screwed, And actually, they are good. Actually, x86 is doing right now good, also in the servers, but you can see like a triple more performance from the same area, while actually having higher IPC, guys. This is not some low performance core like the first ARMs. They were kind of useless, but this is actually delivering higher IPC and this is really dangerous. Let's summarize this video, because I originally planned this video to be 10 minutes long, but it looks like it will have a couple of minutes more. So I hope you enjoyed, and I'm preparing some more videos because we didn't talk about everything. And one of the things is, yeah, we should compare also um, the IPC, actually the rise. This is the performance per clock, or the IPC. And you can see we should talk about uh, the history of the IPC development a little bit more deeper, because it's really exciting here, because you can see the Apple is different level of the development. You can see that the slope is absolutely incredible, because the AMD even is doing quite good job. I am the AMD fan, guys, and AMD is doing great job. Even this 2020, the Zen 3 should be here, so they might go this way. Not bad, right? But I don't know if they will deliver every year new Zen architecture, because they say they have like 18 months period for new architecture. So the AMD will be somewhere here probably, and Intel is bringing next year the Golden Cove, and it should be 380 something, so it should be somewhere here. So we'll see. The Intel is also going this way, but the thing is, you can see from this graph that Apple is going faster, and especially the Cortex core, the line sensible cores, they are going even faster right now than Apple, and they are trying to catch the Apple. And I think the biggest danger is the Cortex cores right now. Even the Apple is the king of the architecture, and the Nuvia will be somewhere here. Nuvia is the new king probably, and maybe. So we'll see. So there are a lot of exciting things is coming for 2021 actually, because there is a Phoenix, there is a A14, and A15 will be somewhere here. Nuvia fighting the Apple A15. This is really exciting. There is coming new Matterhorn from the Cortex cores, and the new Matterhorn is also 2021, and it should be somewhere IPC around 812. So it's really somewhere here, and you can see the new Matterhorn cores. They will outperform in terms of IPC, anything from AMD and Intel, even Golden Cove, even Zen 3, Zen 4. Yeah, it looks really bad for the x86, but when the ARM will come to desktops and the laptops, it's going to be really exciting also for the customers, because we can choose maybe something even better than the x86. So it's kind of it will be really interesting. So yeah, and I would like to also talk about next videos about more comparison about the ARM ISA and the x86, because there is a lot of interesting things also regarding the sim vectors and the matrix multiplications. There is more things we can compare the AVX. There is a lot of stuff I have prepared, and also a special video about the frequencies. We should also talk about the TSMC 5 nanometers, because this is what will be also important for the Apple success, because Apple is going to use the N5, the 5 nanometer I would like to talk also in some other video about the frequency scaling, because the 5 nanometer TSMC process is actually bringing some pretty decent uplifts in terms of density and also frequency. And not this is the basic. There is also other options about the frequency, and the maximum actually is like 35% uplift in the frequency if they use the high performance process. So actually it's really interesting. There is a lot of options and Apple can use right now, and it actually is not using. So a lot of people forget this, and should also discuss also kind of pipeline design, and especially to compare the voltage curves, the characteristics of the microarchitectures, because you can see, maybe you know that there was an experiment. TSMC prepared the Cortex, this A72, which is the Raspberry Pi 4 chip. This is really slow. It has a IPC about where is the comparison? It has the IPC. What is the Cortex A72 here? It's here. Cortex A72 is here. So you can see the IPC in compared to Comet Lake is less than half, and it's running in the Raspberry Pi only 1.5 gigahertz. So, and in the cell phone is running about 2.3, and so it's not really fast chip. And but TSMC actually did kind of experiment, and they did run. Actually, they manufactured this Cortex A72 using 7 nanometer high performance process, which is actually using the Zen 2, and they were actually able to reach 4.2 gigahertz, guys. So this is another evidence that that there is a lot of space actually to increase the performance if they really need to go there, which I don't think, because they would mean completely new masks. It costs a lot of money to make a high performance chip just for the speed, and you will sacrifice the density, of course, and everything. But it is really showing that that the pipeline design of a low power mobile architectures are really similar to the high frequency pipelines, and just operating in different range. You can see here on the Apple, we will compare it here. You can see the curve is pretty nice here, and above 1 volt it's going to spike a lot. So this is the price for high density, because the high density, it just limits you with the frequency, and you cannot go to 1.4 volt. And when you look at the Zen 2 pictures, they can go 1.3, almost 1.4, and we know that the processor actually are spiking somewhere up to 1.5 volts sometimes. So actually it's yeah, the high density costs you really limited range of the voltage, and the high performance process, it allows you to go much higher with the frequency and also with the voltage. So this is really big difference, and it's important to see that the 4.2 gigahertz, which was for the A72. Then you can see 4.2 is somewhere here, and 1.375 volts is actually somewhere here. So, and this is like this chip was not produced in the mass production, so there was no pair functioning, no binning. You can see the binning for the Zen chips is perfect. The best chips, they operate at the 4.2 gigahertz at much lower voltage than the normal chips. So you can see there might be some there is some difference in the pipeline maybe, but roughly it can run really similar frequencies, because 1.2 volt was here. So you can see the Cortex efficient cores are really not the voltage frequency curve is really similar. They can reach really high frequencies if they need to, and if they are manufactured so yeah, this is another thing I would like to talk in some future video. I'd like to also make a video about Nuvia, because Nuvia is really interesting here. Here is the prediction. We talk about it. It will be probably the king of the IPC, even better than the Apple. Let's see. And I will also talk about some video ARM Cortex and do some prediction about the ARM Matterhorn, because the projected IPC actually is like a 60% above Comet Lake. So it means it will be much faster, like a 20% above the Golden Cove, and like a 40% above Zen 3. So next year the ARM Cortex X2, and probably named X2 actually, because this year was the X1. So the completely new architecture Matterhorn will have a really interesting, really incredible IPC, similar to Apple A12, which is also around 60% above the Comet Lake. And this will be available for every Android smartphone actually since next year. So this is really disruptive for x86. So I would like to talk about this in some special video. And yeah, and maybe we should also talk about the Zen 3 prediction, if the 15% IPC above Zen 2 will put you somewhere here, so which means big trouble, because this year announced X1, the Cortex X1 has a much higher IPC than announced that Zen 3, that predicted Zen 3 or suggested, rumored, and to actually, I don't know, it looks to me really bad, because if Zen 3 will have a 20% more IPC, it's still not enough for against this Cortex X1. This is really, I don't know, and the Cortex X1 is actually close to the Golden Cove, and it's coming end of this year and the beginning of the next year, actually, the silicon. So actually you can see the new ARM cores are super powerful, and I would like to make a special video about the Cortex X1 and the Cortex X2, because this is kind of when Apple is kind of Godzilla, or Nuvia and Apple is a kind of Godzilla, and with the monsters IPC, this cheap Cortexes are kind of Velociraptor, or how to say this, really dangerous monsters, and because they can be launched everywhere, also in the servers actually. And for the servers, this will be really danger architecture, also supporting the matrix multiplication, which is really killing feature for x86. So there is a lot of things to talk actually. I hope you like this video, even it's a bit longer than 10 minutes, right? And despite I'm terrible speaker, yes, but please do not share this video much, because especially AMD has a lot of fanatic fans who are really aggressive when somebody tells them that their Zen has a 5% lower IPC than Intel. So you can imagine that how they react to this video, telling them that their Zen 2 architecture has not only 5% lower IPC, but more than 50% lower. So as being AMD fan, it took me a lot of weeks before I was able to accept all these new information. So please do not use this video as a flame starter on some forum, because this is not why I'm making this. And also, please don't give me any likes, because I do it just for fun, from some sharing some interesting information. Because, for example, I was searching for some information about the ARM Cortex X1 architecture this year, and this is quite big change, and I was not able to find any useful deep dive video about this architecture. Because if you look, for example, there is 3 memory units which can do 3 loads, and this is actually the first CPU on the world, as far as I know, that it can do 3 loads per cycle sustainable. And all those guys on the YouTube, they do present this architecture, and nobody mentioned it. This is really big change. This is kind of this means this microarchitecture is pretty challenging, for the high performance. It is no more like some small architecture for smartphone. This is really pushing the performance and the IPC to really big way, and nobody actually, probably they don't care, or they don't have a clue what this means actually. And the same for the IPC, because the IPC, the 30% jump, that's a lot for one generation, and for per year IPC iteration. This is really huge, and nobody makes any conclusion, because they don't have a clue that Zen 2 IPC is somewhere here. It's a little bit slower in the integer. The Zen 2 is a little bit slower than this Cortex 77, which is this blue one. So nobody has clue that the Zen 2 is here, and this Cortex X1 has a more than 30% IPC advantage. And so nobody actually assumes that the Zen 3 with a 15%, maybe 20% IPC uplift is somewhere here. So this Cortex X1 is kind of outperforming Zen 3, and Zen 3 is a big change, and that's why I'm making this video, because when I saw these numbers, I immediately, I saw that, oh, this is the problem, because, or at least for x86, so it's really exciting, and nobody gives some conclusions, and nobody gives some, predictions. Nobody really thinks about it in some broader scope. And another thing is the Matterhorn is coming. This is really another huge change. This is 17 micros per cycle, and this Cortex X1 is 15 micros per cycle. Nobody compares. Everybody is presenting these microarchitecture official pictures, and nobody kind of even thinks about how many micro cycles it is. This is huge, performance in compared to Zen. 2 architecture, and the rumor about the Matterhorn being even wider and having IPC around Apple A12. This is really major thing. This is really huge, and yes, and next year, that's why I'm making this video, because next 2 years is going to be like a golden age of the microarchitecture, and it looks like some people, some CPU enthusiasts, they do know this, but most of the people, especially on the YouTube, they present it like a nothing is happening, but it's happening like a really big changes right now, because the Nuvia is coming next year, the Golden Cove is coming next year, the Matterhorn with the ARM v9 and the matrix multiplication is coming next year. This is huge changes, and also AMD Zen 3 and Zen 4 is coming next year. Actually, Zen 3 is coming this year, but Zen 4 will be probably end of the next year. So next year will be super for the CPU enthusiasts. This is going to be like a golden age. And again, so really exciting things is coming, and that's why I'm making this video. And yeah, I can talk like 2 more hours, so I will end up this video. So guys, I hope you like it, and okay, talk to you soon about some other architectures.